Lisa Pfeffer. I'm an atmospheric volcanologist. I work for the Icelandic Met Office, or Veðurstofa, as it is in Icelandic. My job is to measure the gases that come out of the Icelandic volcanoes, both in between eruptions, which is the vast majority of the time, and during eruptions. And so most of what we're going to be showing you in this video today is measurements that we make during eruptions.
So I'm going to show you the components to a drone multigas, which is provided for us by our colleagues at INGV Catania and the University of Palermo. So this design is unique to them. They build this. And what you can see here is a water trap, and the gases that we're going to be measuring come in here. And this is where the gases come out. I'm going to be opening up the box. Inside the box, we have an SO2 sensor, an H2S sensor, a CO2 sensor, and a humidity sensor. By having this design, which is as lightweight as possible, we're able to fly the multigas on the drone in order to measure the gases that are up in the air.
So today we flew the drone and we made a couple different types of measurements. The measurement that I'm most interested in is we flew a multigas on the drone. And so what we do is we were able to fly with the drone into the volcanic eruption cloud, and then we're able to measure these 3 different gases. And so when we go back, and you'll see this later, we calculate the ratios of the different gases to each other so that we're able to make a triangle plot where we plot the sulfur to the water to the CO2. And by doing this triangle plot, we're able to see if there's a change in the gases that we're measuring in the plume, which could indicate a change in the volcanic system itself. One of the reasons that we're so interested in the ratios of different gases to SO2 is because with the DOAS, as we did a DOAS traverse both today and yesterday, so the DOAS is able to give us the emission rate of the SO2. So when we're able to get the ratio of other gases to the SO2, such as the CO2 or the water, then we're able to then relate this to the flux that we measure with the DOAS and able to get then the emission rate of these other gases that we're interested in. Some of the other measurements that we made today was we attempted to collect a bag sample of CO2 so that we could analyze this back in the lab for the carbon isotopes in the CO2. This is another indicator of the magmatic system and what's happening underneath the ground that we're able to measure in the gases in the air itself. The third measurement that we made today is with the drone itself. And with the drone itself, we were flying both a visual camera and a thermal camera. And with these, we're able to see different features of the eruption cloud and of the lava. And so we're able to use these observations to help relate the gases that we're measuring to the dynamic processes that are occurring within the eruption. Today, the drone that we were flying is a Matrice 210. This is a DJI drone, and it's a drone that is capable of carrying over 2 kilos. And we were able to attach to this drone, which normally flies with both a visible camera and a thermal camera, we're able to attach both the multigas and the bag sampler for collecting the samples for analyzing the carbon isotopes in the CO2. So the multigas and the gas sampler together weigh about 2.1 kilos. And this payload, we've had many successful flights with this drone, but it's also at the limit of what the drone is capable of. And as we saw today, the drone did become unstable and did crash on the side of the volcano. So you need to really make compromises between how many instruments you're carrying and what you can safely do given the unstable conditions around the volcano, the updrafts, the thermal differences, and the strong winds that we have in Iceland. All of these things have led to, as far as I know, there have been several hundred drones that have been lost during this eruption. So it's very difficult conditions for flying, but we have had many successful flights and been getting really brilliant data. So it's a very important tool, which really benefits us greatly, but it also has its downsides and its costs.
Hi, my name is Yves Moussallam. I'm an assistant professor at Columbia University and visiting our friends here at IMO in Iceland. So what we've been doing in these last few weeks, mostly with the colleagues here, is we've been trying to get samples of the volcanic gases that you see behind me. So we're trying to actually get a pristine sample of the gas and bring it back to the laboratory. Specifically, what we want to do with this type of samples is to look at isotope signature of carbon dioxide. So basically we get samples which are going to have some amount of CO2 from the background air, so 450 ppm from that, and some amount of CO2 from the volcano, as high a concentration as we can get. From this type of measurements, if we have enough of them, we can then plot them on the line and basically determine what the composition of the pure volcanic gas member is. We know the pure atmospheric end member, and so our samples are going to fall along a tie line to the pure volcanic end member. So the most concentrated a sample we can get, the better, because the closest will be to our volcanic end member, the lower our error is going to be on our extrapolation. And so that's why we've been trying to get samples increasingly closer to the vent itself. So we started by taking samples with about 30 ppm SO2 above background, so probably 60 ppm CO2 above background. And then we got closer and closer and closer, and eventually we got too close. So the gas sampler itself, the way it works is very easy. So it has a few components. The first component is a SO2 sensor. So this is going to be an electrochemical sensor, exactly the same one that you have in your multigas, for instance. So this is just going to send a little signal. Basically, you're going to have an electric potential which is related to the concentration of SO2 that you're seeing. So we have that in place. We read in real time the amount of SO2 that is in the atmosphere around us. When we get to a threshold value that we set on the sampler before, the sampler is going to activate a little pump. The pump is also the same pump as you have in the multigas, but this pump, instead of, as in the multigas, having the air flowing through a series of sensors, now the pump is only going to get activated and fill a bag. So these are Tedler bags. They are normally used for measurements of air, basically to look at different conditions. And so it's going to fill this bag up to a target pressure that we also set. And so what has been kind of hard was to gauge the right pressure at which to set the bag, because the atmospheric conditions change a lot. And so we've been oscillating between about 1070 hectopascal to just 1000 hectopascal. So you have to kind of change that as you go, because in some days 1070 might be too much, the bag will explode. In some cases it might be too little, the bag will be only half full. But so basically that's how the sampler works. We measure the SO2. When we're above the threshold, we actionate the pump. When the pump detects that the bag is filled, it stops, and then the drone comes back and we have a nice bag full of volcanic gas.